Here all, welcome to NASA's Romance with Chemistry. Keep aside the heart, let's romance with the mind. In today's segment, I'm going to do the topic Optical Isomerism. It is a small topic and it aims to strengthen the basics for PU as well degree. In PU you have isomerism and in degree you have stereochemistry in detail. So this is just a small attempt to strengthen the basics for all the 5 years, that is for PU students as well as for degree students. And the topic is optical isomerism, and let's get started. If you take a monochromatic light or an ordinary light, it is composed of waves, right? These waves vibrate in many different planes. You can see here, these waves vibrate in many different planes, that is in all directions. When this light, monochromatic light, is passed through an equal prism or a polarized lens, it vibrates in only one plane. Now this is called PPL. You can see it vibrates only in one plane, and this is known as plane polarized light. So what you do? You're going to prepare a solution of organic compound and place it in a polarimeter. They rotate the PPL. The PPL which was in single plane, is now rotating. This is known as optical activity, and the substances which rotate the PPL are called as optically active substances. That means those substances which do not have the potential to rotate the PPL or which do not have any interaction with the PPL are called as optically inactive substances. So, what is optical activity? Solutions of some organic compounds have the ability to rotate the PPL. And this optical activity is being measured and detected in polarimeter. The example for optical active substance is lactic acid because it can rotate the plane polarized light. But those substances which do not have interaction with plane polarized light, they are known as optically inactive substances. So now, what is optical isomerism? Two compounds which have similar molecular and structural formula but differ in the direction of rotation of PPL. If there are two optically active compounds having similar molecular formula and structural formula, but they differ in the direction of rotation of PPL, hence they exhibit optical isomerism. So what is meant by direction of rotation of PPL? The rotation of PPL can have two possibilities. One is it can rotate to the right, that is clockwise direction, or it can rotate to the left, that is anti-clockwise direction. So based on that, we have two, that is dextro-rotatory substances and levo-rotatory substances. Those substances which rotate this PPL to the right or clockwise are known as dextro, because in Greek dextro means right, and they are indicated by plus and small d. So example is plus lactic acid or D-lactic acid. Those substances which rotate the PPL towards the left, that is in anti-clockwise direction, because levos in Latin is left. They are known as levo-rotatory and they are indicated by minus sign or small l. The example is the fermentation of starch to ethanol. During this process, you get a product called as 2-methyl-1-butanol. This product has the potential to or ability to interact with the PPL and rotate it towards the left. Hence, it is minus 2-methyl-1-butanol or small l 2-methyl-1-butanol. Here you will have to know that there should not be any confusion between small d, capital D, and small l, capital L. If you are going to see glucose is also optically active, but here the capital D and capital L are not speaking about optical activity. They are not speaking about dextro-rotatory or levo-rotatory. When you see capital D, it means the glucose has 4 chiral carbons. Okay, we will come to know what is chiral carbon. But glucose has 4 chiral carbon. The 5th carbon is the highest chiral center. So, on the highest chiral carbon, if OH is on the right side, it is D-glucose. If OH is on the left side, it is L-glucose. That means these are isomeric forms of glucose. D-glucose and L-glucose are isomers of glucose. They don't have to do anything with respect to the dextrorotatory and laborotatory. If we were speaking about dextrorotatory, then we were speaking about small d, not the capital D. And we were speaking about the clockwise direction of the PPL. So, now you know what is an optical active compound. So, optical active compounds are those which have the ability to rotate the PPL. And this optical activity is expressed in terms of specific rotation. You have seen, you can see here the specific rotation formula. The alpha is nothing but the angle of rotation of the solution. The L is nothing but the length of polarimeter tube. C is concentration of the solution. And lambda is nothing but wavelength of light. And T is temperature. So let's define the specific rotation. Specific rotation is defined as the rotation produced by the solution, the angle of rotation alpha produced by the solution of length 1 decimeter and unit concentration 1 gram per cm cube for a given wavelength of light lambda at a temperature T. So, specific rotation is defined as the rotation produced by a solution of length 1 decimeter and unit concentration 1 gram per cm cube for a given wavelength of light at a given temperature. So, optical activity is expressed in form of specific rotation. So, we have seen that for a compound to be optically active, it should know to rotate the plane polarized light. That is the first condition. What are the other conditions for the optical activity? The second condition is the compound should have minimum 1 chiral carbon or 1 chiral center. The third condition is it should not have plane of symmetry. So, let us deal with the other conditions. What is meant by plane of symmetry? So, I said optically active compounds should not have plane of symmetry. What is plane of symmetry? If you see this compound, this is Meso Tartaric Acid, you can see one red line. Okay, this is a real or imaginary line which divides the molecule into two identical halves. These two identical halves are mirror image of other. This is known as plane of symmetry. Plane of symmetry is, it can be a real or imaginary line which divides the molecule into two identical halves. Each half is mirror image of the other. It is called as mirror plane or sigma plane. So, Meso Tartaric acid is having plane of symmetry, hence it is not a optically active substance. So, it should not have a plane of symmetry. Second is, it should have a chiral carbon. What is chiral carbon? You can see a carbon which is having N, Z, Y and X. These are all 4 different elements or 4 different atoms. So, carbon atom bonded to 4 different atoms or groups in a molecule is known as chiral center. I have shown it with an asterisk mark. Okay, this is otherwise called as asymmetric carbon also. If you take the example of lactic acid has OH, CH3, COOH and H. All the 4 are 4 different groups. Hence, the C is the chiral carbon. So, lactic acid can rotate the plane polarized light, condition 1. Second condition, it has chiral carbon. So, we'll have to see the third condition whether it has plane of symmetry. So, chiral molecules are those which have 4 different groups. They do not have mirror plane or sigma plane. They are non-superimposable on their mirror images, and that is, they don't have plane of symmetry. So, first condition is satisfied, it will rotate the plane polarized light. Second condition is satisfied, it has a chiral center. Third condition, that it doesn't have the plane of symmetry, that is mirror plane or sigma plane, or they are non-superimposable on their mirror images. Now, this, because the lactic acid satisfies all the 3 conditions, it is an optically active compound. Now, what is chiral? Chir comes from the Greek word hand, okay, and it is also called as dissymmetric molecule, and hence only chiral molecules show optical activity. So, that means that any compound, any substance that has one chiral center should be called as optically active. But we have seen that in meso compounds or the Meso Tartaric acid, you saw that in Meso Tartaric acid here, it has 2 chiral carbons. The condition was 1 chiral carbon, but this has 2 chiral carbons. Still, it is not a optically active substance. Why? Because it has plane of symmetry. So, it is called as achiral carbon or achiral molecules. Achiral molecules are those which possess plane of symmetry. That means they are superimposable on their mirror images. So though it has two chiral centers, because it has plane of symmetry, it is not a optically active compound. Hence Meso Tartaric acid is not an optically active compound. So they are meso compounds. What are meso compounds? They do have more than one chiral center. Still they don't show optical activity because they have elements of symmetry. They are achiral molecules. So amongst the Meso Tartaric acid and the lactic acid, we have seen that the lactic acid possesses all the three conditions. Condition 1, it can rotate the plane polarized light. Condition 2, it doesn't have plane of symmetry. Condition 3, it has one chiral carbon. So it is the optical active compound. So now let us deal with the lactic acid and its optical isomerism. So I told you it has one chiral center. Condition 1, it is non-superimposable on its mirror image. It lacks plane of symmetry. Condition 2, and it rotates the plane polarized light. Condition 3, and it exists in three forms. So based on the rotation of plane polarized light, the lactic acid has three forms. One is, if it is going to rotate the plane polarized light to the right side, that is the clockwise direction, it is dextro-rotatory or small d. If it is going to rotate the PPL on the left side, then it is Levo-rotatory, that is anti-clockwise direction, minus or small l. If it is going to rotate, and there is one more form where it is optically inactive, that is it is existing in both plus and minus, that is clockwise and anti-clockwise. So that particular lactic acid, which is an equimolar mixture of both dextro and levo isomer, then it is called as racemic mixture. So racemic mixtures where there is equimolar mixture of dextro and levo isomer of lactic acid is optically inactive. So dextro-rotatory is optically active, levo-rotatory is optically active, but the racemic mixture is optically inactive. So now, what are enantiomers and what are diastereomers? Those substances which are optically active isomers and they are non-superimposable mirror images like lactic acid. They are optically active and they are non-superimposable mirror images. They are known as enantiomers and they have similar chemical and physical properties and they differ in their specific rotation. Diastereomers are those stereoisomers which neither have superimposable nor mirror images and they differ in physical properties and they are separated by chromatography, fractional distillation and fractional crystallization. We are going to go in detail of enantiomers and diastereomers in our next segment. For today, what we have learned is in optical isomerism, we learned about the monochromatic light, then the plane polarized light, and then what is optical activity and how is it measured and how the plane polarized light is being rotated in the clockwise and the anti-clockwise direction, the dextro and the levo-rotatory substances, and what is the difference between isomers and the optical activity, that is the difference between capital D small d and capital L small l. Further, how the optical activity is being measured in the form of expressed in the form of specific rotation, and what are the conditions for a compound to exhibit optical activity. The condition of first, that is rotating the plane polarized light, second being chiral, and third having minimum one chiral, and third is plane of symmetry, which is not having plane of symmetry. Though meso compounds have chiral centers, two chiral centers, still they show plane of symmetry, hence Meso Tartaric acid doesn't fall into the optical active compound. And then lactic acid and its optical isomerism, where we dealt with the dextro-rotatory form, levo-rotatory form and the racemic mixture, and a little insight on enantiomers and diastereomers. Hope this helps for the basic for isomerism, optical isomerism. In next segment we are going to deal in detail the further enantiomer and diastereomers. Thank you.